Example 3.6. In this example, we evaluate the possible existence of an optimum insulation thickness for a radial system. We are going to evaluate an expression for a thin-walled copper tube with given geometry, an internal temperature for refrigerant, and an outside temperature for air. We will evaluate an expression for the optimum thickness for this particular application. Once we obtain the application, we will confirm the results by computing the values with a diameter of 10 millimeters with different values of thicknesses, and the insulation material is going to be cellular glass. This problem is said to be one-dimensional, steady. We will use a cylindrical coordinate system. We are going to assume that the radiation is negligible, and we're also going to assume that the thermal resistance of the wall is negligible. We start the analysis of the problem by defining the thermal resistances. We have a resistance due to conduction and the other one due to convection. Notice that both resistances are functions of R. The reason is we do not know the outside radius, because what we're looking for is the thickness of the insulation. We define the value of the heat rate to be the changes in the temperatures divided by the total resistances. Notice that in this case is only one-dimensional, the radial dimension, so we are not interested in the length of the cylinder. Therefore, what we define is the value of Q apostrophe, which is the value of Q per unit length. In the same way, we could write the total resistance as a function of length, and we could write it in this expression. Since we're looking for the total thickness or the ideal thickness, we want to be able to minimize the value of the total resistance, and that is done by taking the derivative of the total resistance as a function of R. So we could set it up as the total resistance as a function of R, and we're going to make this equal to 0. Then we're going to solve for R, which is going to give us the minimum value for R. If we do the process and we solve for R, we're going to obtain that R is equal to K over H. Please make sure that you do the derivative process and solve for R so that you could get exactly the same result. The next step is to determine whether the value of R is going to minimize or maximize the total resistance. That is done by taking the second derivative of the total resistance with respect to R. So if we calculate the second derivative of the total resistance with respect to R, we find that this value is equal to 1 over 2 pi K to the third H to the second. Notice that this value, all the quantities inside of here are positive, therefore the second derivative is also positive. This indicates that the value of R minimizes the value of the total resistance, therefore maximizing the value of the heat transfer. Therefore, the R becomes an R critical. And we define it as, once again, as K over H. By knowing this, we could find that the thickness of this particular subject is going to be R critical minus the inside radius, and that is going to give us a value of 0.006 meters. Notice that the problem has insulation thicknesses available as 0, 2, 5, 20, and 40 millimeters. The thickness that it was calculated was 6 millimeters. That indicates that any thickness that is greater than 6 will provide enough insulation to the application. However, if the application is lower than 6 millimeters, the heat will be lost into the environment and the insulation will not be effective.